This is the setup we use in our experiments. On the optical axis from left to right, the light source, a nanolight, the collimating lens, the two-dimensional nozzle, and a TV camera with image lens. In detail, the light source. The pulse generator, a parabolic reflector in focus of which a point spark source. The pulses are flat and of the N-wave type. The rotation axis for the pulse source lies on the nozzle tip. The angle of incidence of the pulses can be varied from plus 60 degrees to minus 60 degrees. Once more, an overall picture of the setup. On the right side, the image lens and the TV camera, a plumbicon. The signal of this camera is fed into the electronic apparatus outside this room. Shown here are the electronic components: wave analyzer, synchronization unit, TV monitor, and videotape. In the course of this film, we'll change the amplitude and the angle of incidence of the pulse and the pressure ratio of the jet. This graph shows the pressure amplitude as a function of time of one pulse, an N wave. A shadowgraph, the photonic image of the flat sound pulse that results from one spark ignition. In one pulse, we distinguish two steep density gradients, and so in the shadowgraph, two separate lines. There is no flow. The lip of the nozzle acts as a line source that produces the circular waves. Again, notice that with this technique, there are always two waves instead of one. Now with flow, development of the interaction as a function of time. The pressure ratio is 1.05. The same for a pressure ratio of 1.8. We have also this development at a pressure ratio of 3.5. The jet is stabilized against oscillation by two feedback interrupters. A sensitive shadow technique is used for visualization. The same development at the same pressure ratio, but now visualized by an insensitive shadow technique, which enables us to visualize more in detail the inner structure of the cells and the resulting effects of the interaction process. The phase and the amplitude of the pulse are kept constant. The pressure ratio increases from 1 to 4 and decreases to 1. The shift of the disturbances in the downstream direction is due to the increase of the exit velocity. In the interaction process, the discontinuity, lip-free boundary layer, proves to be the dominant factor. To show this, we did limit the area of interaction near the lip to about 0.2 millimeters by means of a pulse deflector. We start with no flow. Increasing pressure ratio. Over the whole range, the resulting effects are similar. The phase is kept constant. At a pressure ratio of 2, the deflector will be removed. There is no visible change in the interaction results. So, the onset of the interaction, as such, is confined to a very small area at the nozzle tip. We now prevent interaction near the lip and let the interaction take place somewhere downstream. Near the deflector tip, we see no effects. The disturbances that occur when shifting the deflector towards the nozzle tip are due to leakage between deflector and boundary layer. They originate, as calculation showed, from interaction at the nozzle tip. With a fixed pressure ratio and a constant phase, the amplitude of the pulse will be decreased till under the threshold value. We define this value as the amplitude for which visible interaction effects no longer occur. The pressure ratio is 3.5. The amplitude of the pulse increases. In the following items, the angle of incidence of the incoming pulse will be varied. The pressure ratio is 1.8. We follow the interaction as a function of time. The angle of incidence, alpha, of the pulse is equal to 0. The same at a pressure ratio of 3.5. Interaction as a function of time. Confirmation of the dominant role of the lip. Alpha varies from 0 to minus 60 degrees. Variation of alpha from minus 60 degrees back to plus 60 degrees. Alpha is equal to plus 60 degrees. The phase changes continuously. We follow the interaction as a function of time. With the aid of a pulse reflector, we can observe in succession the interaction process with the pulses going up and going down. The same, but now at a pressure ratio of 3.5. It is clear that in the case of alpha is equal to minus 60 degrees, the interaction results are more violent than when alpha is plus 90 degrees. Now we concentrate our attention to the interaction results inside the boundary layer and furthermore in the main stream. The multiple reflections are clearly visible. The pressure ratio is 1.8. The rate of change of the phase, either in the positive direction or in the negative direction that is chosen, depends on the details we want to observe in the flow field or in the sound field. Clearly visible are the resulting effects. Important to observe is the deformation of the MAC lines as a function of time. This deformation is induced by the infalling pulse and starts without delay from the nozzle tip. The same at a pressure ratio of 2.6. With a constant phase, the pressure ratio varies from 1 to 2.6. Periodic movement of nozzle tip MAC lines in the case of natural vibration. This is comparable with the movement when using the externally generated pulses, which shows that the external pulse technique is suitable for detailed studies of natural vibration jets. Phase difference between left and right is 180 degrees. Angle of incidence plus 90 degrees. The same in the case of forced vibration. The angle of incidence is minus 60 degrees. The natural vibration of the jet is suppressed. On the right side, an externally generated pulse. The interaction results are comparable with the forced vibration case. The time is reversed again and again to be able to visualize the time correlation between interaction and its results. Mark the deformation of the MAC line. It is clear that the onset of oscillation starts at the nozzle tip directly after the front of the pulse passes by.